Hi everybody. So we were in the middle of description of beginning description of entropy due to Claude Shannon. Okay. And Shannon wanted to describe or associate disorder and entropy. And eventually his idea is that I somehow need to associate the number of states that I have in the system, the different probabilities of being in those different states with entropy and disorder. So he postulated several requirements for the disorder. Okay, what is a disorder? And eventually all those requirements somehow circulate around the distribution of f of I. What is f of I? The probability of a system to be in state I. We know, or we assume, that this distribution somehow should tell us what is the disorder. Okay? We need a definition, a mathematical definition of the disorder. We know something about disorder. For example, we know that if we have only one state, okay, then there is only one fi, which is 1, and everything else is 0. So the system is not disordered, right? So this is at least the minimal disorder that we can have in the system when we have only one state. The more states we have, the more occupation probabilities are, okay? The more disordered the system is. So let's write down the postulates of Shannon for the disorder. Okay, so this is requirements for a measure of disorder. So first of all, A, we need that the measure of disorder, the measure of disorder should be described, be entirely described by all those f of I. Okay, so those probabilities should completely define the disorder or the measure of disorder. B, what else do we know? If any of the fi is 1, okay, so if we have at least one probability of all this group that is exactly 1, the measure of the disorder is 0. The measure of the disorder is 0. Okay. C, the maximal measure of this disorder is achieved when the system can be anywhere, okay? Anywhere with the same probability. Okay, what it means? It means that I have omega, which is the total number of states that I have in the system. Okay, the claim is when I can be anywhere, okay, I'm spreaded for the maximal spread. Okay, I can be at any given state of my system, and the probability to be in this state equals to any other state. Okay, then Shannon claims then I will achieve maximal disorder. What it actually means? It actually means that for maximal disorder, f of I simply equals to 1 over omega. Because all the probabilities are equal to each other, right? I have total omega number of states, and then I have to have the total probability is 1, so I have to have that each of the probabilities is 1 over omega. So we reached D. The maximal disorder is an increasing function of omega. Okay. The more states I have, the more disordered I am going to become. Okay. E for two systems with disorders or with measures of disorder D1 and D2, the measure of disorder for a combined system is G1 D1 plus G2 D2, where G1 is the probability to be in system 1 and G2 is the probability to be in system 2. So it's some sort of a linearity, right? Some sort of a linearity of the disorder. Which is basically saying, well, what is the disorder? Disorder is described by the different probabilities. So if I want to be, what is the probability if of the combined system to be in a given state? It should be given by this probability G1, and D1 somehow tells me what is the probability of being in a given state in system number 1. All right. A, B, C, D, E. And we don't have F. Okay? So Shannon had this postulates for what the disorder should be. Okay? And using all of this, Shannon had written the definition of disorder for a given system. And this definition is that we should have some constant, minus k. Okay? What is the constant? K is some positive constant. Okay? Sum of I, so we sum over all the possible states that we have in the system. Fi log of Fi. Okay? This is the definition so when Shannon uses all his postulates of what the disorder should satisfy, eventually he came up with this one single function. Okay? And this k is just some general constant. And what we would see that in order to identify this measure of disorder with an entropy, we only have to use this instead of a general k, k Boltzmann. Okay? One specific constant. So let us see if we have indeed some sort of association between the disorder due to Shannon and the entropy. Okay? Why to define it like this? Can we add some other postulates in order to define the disorder in a different fashion? Yes, we can, but those are quite the minimal ones. You see, it's in some sense like defining a metric on a system or a topology on a system. Okay? I can invent many different metricas, topologies, how to measure distances for a given system. Okay? Usually they have to satisfy some specific postulates. If those are my postulates, I only have this solution over here, and one can prove it. So let us see what is the entropy or the disorder for the two ensembles that we have been using so far. The first ensemble is the microcanonical ensemble, right? So disorder for microcanonical ensemble. Okay. So what do we know? Fj is 1 over omega. Okay? So D is minus k Boltzmann, sum of j. Okay, I'm going over all the states that I have in my system. Fj log of Fj equals to, now I'm substituting this guy inside the equation, so it's minus k Boltzmann, sum of j, 1 over omega, log of 1 over omega. Okay. I can take those two guys out, and I have that it equals to k Boltzmann log of omega 1 over omega sum of j, and I have 1 over here, right? What is this sum over here? This is simply omega, right? The total number of states, okay, that I have in my system. So I obtain that D equals to k Boltzmann log of omega. But what is this k Boltzmann log of omega for what? For microcanonical ensemble. We have seen it at least twice. This is exactly the entropy of the microcanonical ensemble. So we see that at least for the case at least for the case of microcanonical ensemble, the measure of disorder is exactly the entropy of the system. Okay? So the entropy describes to us how disordered the system is, right? At least for microcanonical ensemble. Moreover, what we do see from here, we see that according to the postulate C, the maximal measure of the disorder is achieved when the system can be anywhere with the same probability omega. So basically, for any system, the microcanonical ensemble describes the situation when the system is disordered in the most possible fashion. For a given amount of states, the states are described by the system itself. The ensemble is something that we impose on top of the system, the distribution of how the system changes from one state to another. And we see that the microcanonical ensemble basically describes the situation with maximal entropy. All right, let us do the same for canonical ensemble. So what we do here, okay, so the disorder for canonical ensemble, the only thing that we do is we change the definition of what are our FJs. So disorder for canonical ensemble. All right, so f of j equals to 1 over z e to the power minus beta ej, right? We need to know what the partition function is, and we need to know what is the energy is in order to describe the probability of the system to be found in state number j. Okay, so let's see what is the disorder, which is again minus k Boltzmann, sum of j, f of j log of f of j, it equals to minus k Boltzmann, sum over j. Inside here, what I have 1 over z e to the power minus beta ej log of 1 over z e to the power minus beta ej. Right? Let's go over here and see what we have. Okay, what we have inside is as follows. Okay, so what is log of 1 over z e to the power minus beta ej? It simply equals to log of z minus beta ej. Yep, since reasonable, so we have this equality over here, minus k Boltzmann, 1 over z I can take out of the summation. Inside I have summation over j, e to the power minus beta ej, multiplied by log of z.
Is it minus log of z?
Yeah, it was minus, no, but it's log of z, not log of, oh, it's minus, yes. Yep. So minus log of z, right, minus beta ej. Okay. So let us see. So it equals to k Boltzmann, 1 over z, log of z, a sum of j e to the power minus beta ej, okay, and we also have plus 1 over t, 1 over z, a summation of j ej, okay, e to the power minus beta ej. Okay, so what we obtain over here, what is this sum over here? It's simply z. So we have z and we have 1 over c. So we have k Boltzmann, log of z. Okay, and here we have plus 1 over t, a sum of j, ej, you can call it this fj. And if you look of what we have written on Sunday, what is the entropy for the canonical ensemble, this is exactly the expression that we got over there. This is again the entropy for the canonical ensemble. We've got this expression on Sunday. Okay, how we got it? We know what is the free energy. Okay, and free energy it's E minus T of S, and then we expressed E in this form over here. Okay, and eventually we obtain this formula. So what we see that for canonical ensemble, the measure of disorder is exactly the entropy. For the microcanonical ensemble is the same. The disorder is exactly the entropy. So what we see is the entropy for any given ensemble is going to be given by a different expression. Why? Because the FJs are different for the two ensembles. The measure of disorder is always the same. It only depends on the probabilities. Define for me the probabilities of a system, define for me the ensemble that you're using, okay, and I will calculate the entropy. The formula for the entropy is never going to change. It's exactly this measure of disorder due to Shannon. Okay? So when I want to describe how the system is spreaded, okay, this is a very good measure, and it coincides with the entropy, the thermodynamical quantity that we were using so far. This is why we're talking that the amount of disorder is increasing as a function of time. The entropy is increasing, right, as a function of time. This is part of the laws of thermodynamics. And why it's disorder? Because of this convention that we described to you over here. Now, we can also state something even stronger. What we can say, well, what we know for thermodynamics. From thermodynamics, we know that entropy is maximal in equilibrium. Okay? So we can say the following. Can we start with this definition of entropy, right? Let's assume that the entropy is minus k Boltzmann, okay, sum of j, f of j log of f of j. This is entropy. Now we know that in equilibrium, entropy is going to be its maximal value. This is the second law, or the consequence of the second law of thermodynamics. Okay. Can I obtain some sort of information about the fj's, okay, if I know that the entropy is going to be at its maximum? Okay. Now, generally, I don't have enough constraints in order to answer this question, but I can constrain myself and answer the following question. What are the given fj's, okay, such that this quantity, my entropy, is maximal, and I have two additional constraints. First constraint is just the normalization. The sum over j over fj's should be equal 1, right? Because the probability to be anywhere should be 1. Okay? Another constraint is, well, let's assume that our average energy is constant. Okay? So a sum of E of j, f of j, equals to u. Okay? So it's a constant value. Okay? Now, those are already some sort of a, so this is pure math, this normalization over here, but this is already some physical constraint, right? We know that there is some postulate or second law of thermodynamics. We have invented this formula for the entropy, and now we want to determine what are the different fj's under the constraint that the energy, on average, is constant. Okay? So what we are going to do right now, so we're going to find the maximal value under which fj's s is going to have maximal value. So how it's usually done? So we want to find the variation of s. What is the variation of s? We basically take the derivative of s with respect to all the different fj's, okay, and we compare this derivative to 0. Right? We have done this already at least one time. So delta of s equals to what? It equals to minus k Boltzmann, okay, sum of j, a delta of fj log of fj. What this delta here is, it's basically a derivative with respect to fj. It equals to minus k Boltzmann, sum of j, log of fj, plus 1. All of this multiplied by delta fj. Okay? And we are looking for a solution where everything here, this variation, equals to 0. Okay? Now, this is not enough. Why it's not enough? Because we have those two additional constraints. Right? We have this guy, and we have that guy. So we're looking for a maximal value or a minimal value under two specific constraints. What kind of technique we are going to employ? Lagrange multipliers. That's lambda, yes. Okay, so you remember Lagrange multipliers? Yeah. Okay, so what are Lagrange multipliers? We are saying the following. Delta of sum of j, f of j, equals 0. Okay, so we are going to use that sum of j, delta f j, equals 0. Okay, and we also have the delta of sum of j, ej, fj, equals 0. So sum of j, ej, delta fj equals 0. So the technique of Lagrange multipliers is to say, well, this is your equation that you want to solve. You have two additional constraints. So let's introduce these lambdas that says the following. We have minus k Boltzmann, sum of j, log of fj plus 1, delta fj, plus lambda 1 this constraint, sum of j delta fj, plus lambda 2, the additional constraint, which is sum of j ej delta fj, and all of this equals to 0. Okay? So two constraints, we introduce two constants, lambda 1 and lambda 2. We should determine them later. Okay? And the solution of the minimal or maximal value is obtained for under those two constraints, is obtained when we find the solution to this equation over here. Now, the moment we introduce those constraints, all the different fj's are independent, right? Because we introduce the constraints directly into the equation. Okay. This is the purpose of this constraint. So we have minus k Boltzmann, sum over j, and inside we have log of fj plus 1 minus lambda 1 divided by k Boltzmann multiplied minus lambda 2 multiplied by ej delta fj equals to 0. Okay? Now we're now assuming that all the different fj's are independent. So this sum, okay, though this formula is satisfied where all these summands, okay, whatever is standing in this between those parentheses over here, it equals exactly to 0. Okay, so log of f of j plus 1 minus lambda 1 divided by k Boltzmann minus lambda 2 ej equals to 0. Okay. Now you see we only have one single fj over here. So fj equals to e to the power of what we have, lambda 2 divided by k Boltzmann. So we have over here e to the power minus lambda 2 divided by k Boltzmann ej, okay, or plus lambda 1 divided by k Boltzmann minus 1. Okay. So lambda 2 and k Boltzmann are exactly the same. Minus 1 are constants. K Boltzmann is a constant. Lambda 1 is a constant. K Boltzmann is a constant. Minus 1 is, of course, a constant. So we write this down as fj equals to e to the power minus 1 plus lambda 1 divided by k Boltzmann multiplied by e plus lambda 2 divided by k Boltzmann ej. Now this reminds us of something, right? What does this fj remind us of? This looks exactly, almost exactly, as the fj for canonical ensemble. fj equals 1 over z e to the power minus beta ej. Okay, 1 over z is a constant of the system. Here we have exponent of what? Of a constant, right? Multiplied by eg. Why constant? Because when we developed the canonical ensemble, remember our requirement was that the temperature is constant. Okay? Here we obtain exactly the same result using the second law of thermodynamics for maximal entropy. Okay? We're saying that the entropy at equilibrium should be maximal, and our entropy is provided to us by this formula. Okay? Using the constraint that the average energy is constant. Okay? This was the constraint. Now, here we have a complete freedom to choose lambda 2 and lambda 1. Okay? So we can say that when we choose lambda 2 equals to K Boltzmann, or I'm sorry, minus 1 over T, okay? And we can choose e to the minus 1 plus lambda 1 divided by K Boltzmann as 1 over Z. Right? Those are, the temperature is constant, right? These guys are also constants. The lambda 1, K Boltzmann is constant. So we are obtaining exactly the canonical ensemble, or the probabilities for canonical ensemble, by using only the principle of maximal entropy. We needed this step, last step over here, because temperature is some thermodynamical measure. Okay? We cannot obtain it from just looking on this formula and say, yes, we know what temperature is. No, we don't know what temperature is. We know that it's a constant, right? At least for this representation. It's going to be constant when the total energy is constant, right? So it's something that we cannot obtain from the math. We need the physics and the knowledge what canonical ensemble looks like. But we do see that the formulas, mathematical formulas, are exactly the same. So I don't know what are the meaning of the different constants, lambda 1 and lambda 2. Okay, I need the other way in order to describe them by using physical quantities like temperature, partition functions, and etc., etc. But the mathematical formula is exactly the same. So what we can say is that canonical ensemble is a representation of any given physical system, okay, when the average temperature is constant. The only thing that I need to know is what is the form of entropy. Okay, so when I start from this form of entropy, a very general form, and I only assume that my average energy is going to be constant, I will get this canonical representation. Okay, so this is already nice, and we are learning something about, well, the meaning of disorder and the meaning of maximal disorder. It basically dictates to us how the system is spreading over all its possible states, and it has to spread in this form when the average energy is constant. We can think of another representation, right? So here we started with two constraints, right? So the first constraint was just simply the normalization. This is pure math. The second constraint was the average energy is constant. Now we can think of additional constraints, right? For example, I can think of the constraint that the average, not energy, but the average number of particles is also constant, right? It's a fair physical assumption. I'm looking on the system. Here, I don't know what happens to the particles. Okay? Actually, for this system, the number of particles was exactly constant, in the same sense as the energy for microcanonical ensemble was exactly constant. You remember we started with microcanonical ensemble. For microcanonical ensemble, we stayed the energy is constant, okay, or the temperature, and we arrived to the to this quantity that the average energy is constant. But the energies can be very different. We can step another. We can do another step forward and say, in canonical ensemble, the system was closed. It exchanged heat with the outside world or with the reservoir, okay? But the total number of particles inside the system was closed, okay? And it can impose some difficulties on computing the partition function or performing computations, in the same sense as constant energy impose difficulties on computing the partition function and functions of state. So we can say, well, let's lose this assumption also. Let's assume that our system is not closed. And it can exchange energy with the outside world, and it also can exchange particles with the outside world. And actually what happens in every real phys system. So if I take this marker, okay, the number of particles on the surface is constantly changing. Some particles are arriving from the air, some particles are departing. I can say, well, those fluctuations are negligible. Those fluctuations are negligible, but assuming that there are fluctuations can be very beneficial for mathematical representation, for calculations. Remember, constant values, they impose something which is very, very difficult. the total number of particles, the energy is constant. It was difficult because we had all this counting problems, okay, and they are gone out of the window the moment we say, well, on the average it's constant. Let's do the same with the average number of particles. We won't assume that the total number of particles is constant, but sum over j, nj, f of j is average, it's equals to average n. Okay? So what I'm assuming over here, I'm assuming that my system, okay, can exchange particles with the outside world. Okay? I'm assuming that my entropy is provided to me by this formula over here. Okay? And I'm using the thermodynamics laws to say, in equilibrium, this quantity over here should provide to me maximal value. Okay? Which means exactly as I derive this deltas, etc., for previous case, when I was using those two constraints, let's do the same trick or the same calculation where we're using not two constraints, but actually three constraints. Okay? So delta S is exactly as it was before, right? So the variation of S, I'm looking for maximal value of S. The variation of S is exactly as it was before. The variation of f of j's is exactly as it was before. This variation of sigma of j, ej of j is also 0 as it was before. I only add this additional constraint of delta of sigma j nj fj equals 0. So I have here a sigma of j nj delta fj equals to 0. Okay? This is the only additional thing that I must put inside, okay, in order to assume that I have different values of the number of particles in the system. Okay, so what happens? So let's see, this is, let's erase this. So we have the following situation. We have minus k Boltzmann, sum of j, log of fj, plus 1, delta fj. We have plus lambda 1, okay, plus lambda 1, sum of j, delta fj, plus lambda 2, sum of j, ej, delta fj, plus lambda 3, sum of j, nj, delta fj. All of this equals to 0. Okay? This is the equation that we must solve. This is delta fj. Okay, so exactly as in the previous step, we just sum up all of those guys. Now the fj's are completely independent. So we have minus k Boltzmann, sum of j. Here we have log of fj plus 1 minus lambda 1 divided by k Boltzmann minus lambda 2 divided by k Boltzmann ej, okay, minus lambda 3 divided by k Boltzmann nj. All of this multiplied by delta fj, and this equals 0. And we know that this guy equals 0. Okay. This is what we know. So again, we need to solve an equation that includes only one fj and a bunch of different constants, but now we also have ej and nj. Okay, so what we have, this is a log. So we have log of fj equals to minus 1 plus lambda 1 divided by k Boltzmann plus lambda 2 divided by k Boltzmann Ej plus lambda 3 divided by k Boltzmann Nj. Okay, so Fj equals to e to the power minus 1 plus lambda 1 divided by k Boltzmann multiplied by e to the power of plus lambda 2 by k Boltzmann Ej plus lambda 3 divided by k Boltzmann Nj. This is as far as this method can take us. Remember, previously we also got to some equation that looked like this. We need some physical knowledge in order to determine what are lambda 1s, what are lambda 2s, what are lambda 3s. So lambda 1 is related to this situation where sum of Fj equals to 1. So this is related to the general normalization constant. It's independent of Ej and Nj. Ej is the energy in state J, and Nj is the number of particles in state J. Previously I was using only energy to determine a state. Now I'm using number of particles and the energy to determine the state. Now lambda 2 previously we associated it with minus 1 over the temperature because we knew what the answer it should be. So lambda 2 was a constant, and remember for the canonical ensemble, temperature was constant. What do I mean by temperature constant? So we allowed exchange of heat between our system and the reservoir, but we imposed that the temperature of the system and the reservoir is going to be constant. So this is how we determined lambda 2. Here we still don't know, but we will see that it's also related to the temperature. And lambda 3, we actually we have no idea what lambda 3 is from this perspective. We only know that the form for this ensemble, the new ensemble that we dictated, it's of the following expression over here. We can probably associate this guy as 1 over z. Okay? We will see that here it's e to the minus 1 over beta Ej. Okay? And we will see that this guy is beta. Yep. Minus beta. And here we will see that this guy is plus mu divided by mu multiplied by beta Nj. What this mu is? The chemical potential. Okay? We don't see it from here. Why? Because here it's only math. It determines the form, but it does not tell us what are the constants. Okay? We need the physical interpretation in order to obtain those constants, like beta, which is 1 over k Boltzmann temperature, and mu, that is chemical potential. But we can reason in the following fashion. Lambda 2 for the canonical ensemble was obtained from the knowledge that the average energy is constant, there is exchange of heat, and the temperature was constant. So there is association between the energies and the temperature that determines the average, what is the average energy is. Here NJs, okay, so in this new ensemble, we also allow for exchange not only of heat, we allow for exchange of particles. Temperature determines how the heat is exchanged. Chemical potential determines what? How the particles are exchanged. And so this is why we're going to obtain here this chemical potential. We don't see it right now. We need to derive this ensemble from scratch in the same sense as we derive the canonical ensemble. What we are going to find that this guy over here is exactly something which is named grand-canonical ensemble. Okay? And exactly how to derive those constants, lambda 2 and lambda 3, we will see next week. Thank you.